video, I'm going to be going through test number 3, which was on the 3D unit. So in question number 1, it's asking us which drawing cannot be a cross-section of a cone. So from the base, we see that we can get a circular part, so I'm going to cross that one out. If we cut on a slant, we can get the shape that is in answer choice number 3. If we cut vertically, we can get a triangle. There is no way that we can get a square out of this cone. And in order to make it a little bit more visual for all of you, I have a cone over here. So this is parallel to the base. Notice how it's always circular. And then if I go on the slant, we see the different shapes that result. And then finally, perpendicular to the base, we have a triangle. So no squares coming out of there. For number 2, it says a plane intersects a hexagonal prism. The plane is perpendicular to the base of the prism. Which two-dimensional figure is the cross-section of the plane intersecting the prism? So anytime we have a prism parallel to the base, the cross-section will be the same as the base. So parallel to a hexagonal prism would be a hexagon. Perpendicular to the base will be the same as the faces, which would be a rectangle since this is a prism. And if you're having trouble visualizing that, over here, I have my hexagonal prism, and parallel to the base, no matter which way you hold the prism, you could have drew the prism sideways, it would be the same thing. Parallel to the base will always be the same as the bases. Perpendicular to the base will be the same as the faces. So we can see here why rectangle is the correct answer. Moving on to the next one. Which pair of edges is not coplanar in the cube shown below? So what it's asking for is which pair of edges are not on the same plane? Which one can we not draw a plane for that has the edges on it? So taking a look answer choice by answer choice, EH and CD. So those kind of cross over each other, so I'm not really seeing how we can draw a plane that has both of these on it. So I'm going to put maybe like a check mark next to it to let us know that this might be the answer choice. Let's check out the rest. For number 2, AD and FG. Well, at first glance, it doesn't appear that these are on the same plane as each other. But if I connect the endpoints diagonally, I see that they are on the same slanted plane as each other. I didn't connect that so well. Let me try that again. There we go. So they are on the same slanted plane as each other. So we can draw a plane that has both AD and FG on it. Moving on, DH and AE. DH and AE. Clearly, they are on the same plane. We can easily draw that plane. So that's not the correct answer. And then finally, AB and EF. I can pretty easily draw that plane as well. So those are on the same plane as each other. So that leaves us over with answer choice number 1. I tried, but I could not find a plane that EH and CD were on together. The diagram below, AB is perpendicular to plane AEFG. So we know that perpendicular lines form right angles, so I'm just going to draw that into the diagram. AB is perpendicular to AEFG, so where they intersect, a right angle is formed. The question is asking which plane must be perpendicular to plane AEFG. Well, based on the given information, I see that this plane forms a right angle with this plane. So that would be answer choice number 1. ABCE is perpendicular to plane AEFG. I was up to number 5, right? Yes. Okay. A student has a rectangular postcard that he folds in half lengthwise. Next, he rotates it continuously about the folded edge. Which three-dimensional object is generated by the rotation? The answer to this one is cylinder, which is answer choice 3 here. Anytime you have a rectangle and you rotate it until it becomes a 3D object, it will become a cylinder. You can see this by taking a piece of paper and folding it. And when you fold the piece of paper, you get a cylinder. Here I have a visual to show you how a cylinder is formed by rotating a rectangle continuously around a line. So just keep watching as we rotate the rectangle around and around and around. It becomes a cylinder. And we can undo that. We can unrotate it all the way back around. And look, it's a rectangle. I'll do that one more time so you can see. There we go. An isosceles right triangle, whose legs measure 6, is continuously rotated about one of its legs to form a three-dimensional object. And it's asking us for what the three-dimensional object is. So I think isosceles right triangle is what threw a lot of people off about this. But remember that an isosceles right triangle is just a 45, 45, 90 triangle because it's a right triangle that has 2 equal sides and 2 equal angles. So that's a 45, 45, 90 triangle. So the legs of the triangle each measure 6 because it is an isosceles right triangle. And it's continuously rotated around one of its legs. So it doesn't matter if we rotate around this leg or this leg. I'll just rotate around this leg, I guess. Just keep in mind that both of the legs have a length of 6. I just don't want that to be in the way. I'll write it here on top instead. So if I take this right triangle and I rotate it around the leg again and again and again and again and again, well, the straight line part is going to start looking more curved, just like when we filled the rectangle to get the cylinder. And we're going to start seeing the triangle all throughout on all sides of the line as it's spinning around and around and around. And we can see that the resulting shape is a cone. And we can see that the height is 6. Let me move that back here now that I'm done drawing. So that was the original length of the leg, that was 6. And we can also see the radius is 6 because this is the original length of the other leg of the triangle. So we see that the height is 6 and the radius is 6. The full diameter would be 6 plus 6, which would be 12. So the answer choice that we're looking for is number 4, a cone with a diameter of 12. And just to make it more visual for you guys how we get a cone from a right triangle, here I have a right triangle and we're just going to spin it around and around this leg over and over and over again. And when we do that, when we spin it around and around and around and around, it looks like a cone. We can unspin it and see it started off as a right triangle. I'll do it one more time so you can see how when you spin it, it turns into a cone. For this one over here, we're told that the top of the tent is a square pyramid. And we need to find the volume of all the space that the tent occupies. So we also have to include the bottom part of the tent, which is a rectangular prism. So we're going to have to find the volume of the square pyramid. And we're also going to have to find the volume of the rectangular prism. So anytime we're finding the volume of any pyramid, the formula is 1/3 area of the base times the height. So it's a square pyramid, and let me just erase the markings here so we can see it more clearly. So the top is a square pyramid, and the square part, the square base, has a length and a width of 8. And I got that from down here. This is 8, so this is 8, this is 8, so this is 8. So to find the volume of the pyramid, we need 1/3 area of the base, while the area of the square base is length times width, which is 8 times 8. So I'm going to put that here, 8 times 8, times the height of the whole pyramid. And the height of the whole pyramid is 3. That's the perpendicular line going from the top of the pyramid down to the base. So if I put this all into my calculator, I have 1/3 times 8 times 8 times 3, and I get 64 feet cubed because I'm talking about volume here. Okay, now for the rectangular prism, volume of any prism is area of the base times the height of the prism. So since it is a rectangular prism, or a rectangular prism, I would say maybe a square prism because these are both the same. Either way, it's a prism. So the area of the base would be 8 times 8, so it's a square. So I should have wrote square prism. 8 times 8, length times width, times the height of the whole prism, which is 9. This goes from the top of the prism down to the base. And if I type this into my calculator, I have 8 times 8 times 9, and I get 576 feet cubed. Now, if I take this and add the volume of the pyramid, I should get my final volume, which is 640 feet cubed. So that's the volume of the entire tent. Okay, we needed to find the volume of the entire storage tank here. Let me just make sure I rounded this one according to the question. Yes, nearest foot, we rounded to the nearest foot. It worked out to be a whole number anyway. So we need to find the volume of the storage tank. So the storage tank is made up of two parts, as the question says. It's made up of the cylinder on the bottom and the hemisphere on the top. So we're going to have to find two volumes here. We need the volume of the top hemisphere, and we're also going to need to find the volume of the cylinder on the bottom. So volume of a sphere is 4/3 pi r cubed. So the radius would be from here to here. And since the diameter on the bottom here is 8, half of that would be 4. So I know the radius here is 4 as well. I'm going to plug in 4/3 pi 4 cubed, and just simplifying it on my calculator, that would be 4. Oh, before I put it into my calculator, it would probably make more sense. Since it's a hemisphere, it's half of a sphere. So I'm going to divide it by 2 when I put it into my calculator as well. So we have 4/3 pi 4 cubed. I'm going to put that into my calculator. Then I'm going to divide that by 2. And I get that the volume of the hemisphere part, that's the top, is approximately 134 point, and let me keep a couple of decimal places for now. We don't want to round early until the very last step. Otherwise, it's very likely we're going to end up with a rounding error. Volume of any cylinder is pi r squared times height. So the radius, as we spoke about, is 4. And the height of the entire water tank is 13, but that's from the top of the hemisphere down to the bottom of the cylinder. We just need the height of the cylinder. So since the radius was 4, all we need to do is take away that 4 from the total 13, and we're left with 9 for the height of the cylinder. So from here to here, the height is 9, and 9 plus 4 makes the total 13 of the entire water tank. So we're going to times that by 9. Putting that into my calculator, I have pi 4 squared times 9. and the volume is approximately 452 point. Let me keep a couple of decimal places. Remember, don't round into your very last step. Now I'm just going to add the two volumes together. So I'm going to add the volume of the cylinder to the volume that we got from the hemisphere. And this is where we're going to round according to the question because we're done to the nearest cubic meter, which is whole number. So the volume of the whole water tank is approximately 586 meters cubed. For question number 9, a contractor needs to purchase 500 bricks. The dimensions of each brick are 5.1 by 10.2 by 20.3, and the density of each brick is 1,920 kilograms per meter cubed. The maximum capacity of the contractor's trailer is 900 kilograms. Can the trailer hold the weight of 500 bricks? Justify your answer. So you can't just write yes or no. You actually had to show work to show why you got the answer that you got. Otherwise, it would be all the points off except for one. And that's how the Regents grades it as well. If you just put an answer and no work, you get only 1 point out of all the points that the question's worth. So first I need to find the volume of the brick to find out how much space each brick takes up before I can figure out what the weight is going to be. So I have the dimensions of the brick, and these dimensions are in centimeters. Always a good idea to see what the dimensions are. So I'm going to multiply 5.1, what the units are, times 10.2, times 20.3. And when I hit enter, and I should write something over here. So 5.1 times 10.2 times 20.3. And for the volume of each brick, I'm going to write down all the places for now. I got 1,056.006. So now I need to find out the weight of the brick so I can find out if the trailer can hold all the bricks. First, I need the weight of one brick, then I can find out the weight of 500 bricks. So they give us the density of each brick. And I know that density is equal to mass over volume. So I have the density. It's 1920 kilograms per meter cubed. And I want to figure out what the weight is, what the mass is. So I don't know that. So I'm going to leave that as X. And I have the volume. But the thing is that my volume, all the units that I was multiplying before were in centimeters. So my volume's in centimeters cubed. But my volume unit on my density is meters cubed. So before I can plug my volume into my density formula, I do have to convert from centimeters cubed to meters cubed. Now, to go from centimeters, it's not writing properly. Let me fix that. 1 second. To go from centimeters to meters, we just need to divide by 100. But the thing is here, we're not going from centimeters to meters. We're going from cubic centimeters to cubic meters. So you can't just divide by 100. You'd have to divide by 100 cubed. And that was a mistake that a lot of people were making. In order to avoid that, if you saw at the beginning when you were reading the question that you were going to have to convert from centimeters to meters, you could have just taken each of your dimensions here of the brick and divided them by 100 to begin with and avoid having to do this after you get your volume. So once again, you could have just taken each of the dimensions divided by 100 before multiplying them together, and then your volume would already be in meters cubed, and you would avoid having to do this. So on my calculator, I'm going to divide by 100 cubed, and I get 0.001056,006, and that's now in meters cubed. So I'm going to plug that into my volume formula. I have to write that whole thing down again. Okay. Now, since we have meters cubed in the numerator and in the denominator, that unit cancels out, and we're left over with kilograms, which makes sense because that's our mass unit and we're finding the mass. So I'm just going to cross multiply. We can put this over 1 and cross multiply. So I'm going to multiply these two together to figure out what the mass is. So let me multiply by 1920 in my calculator, and I get 2.02753,152. Now, I don't have enough space here, so I'm going to have to start using whatever space I have on this page. So this is the weight of one brick, but we need to figure out if 500 bricks can fit in the trailer. So I'm going to take the weight of this one brick and I'm just going to multiply it by 500 to get the weight of all the bricks. And I get, oops, for some reason, sometimes it doesn't want to write on here. Okay, so I get 1,013.76576. And that's in kilograms. And 1,013 is definitely over the 900 that the contractor's trailer can hold. So the answer is no. The trailer cannot hold the weight. But remember, you couldn't just write that. You needed to show work to back it up. For this next one, a lot of people were explaining why the two stacks of quarters had the same volume, but weren't using Cavalieri's principle, and that's why you probably got points off for this one. So Cavalieri's principle has a couple of components. So what Cavalieri's principle says is that if two solids have the same cross-sectional area throughout, so what that means is that if we're looking at two solids that have the same cross section parallel to the base as you go down, then they will have the same volume as long as they have the same cross sectional area and they have the same heights. So here we have two cylinders. This one's standing up straight, it's a right cylinder. And this one is like with the quarters coming out of it slanted. We call that an oblique cylinder. But they're the same shape, they're both a cylinder. So they'll have the same cross sectional area parallel to the base, no matter which quarter we pull out as we go down. If we pull out a random quarter parallel to the base as we go down, the cross section is going to be circular, the same as the quarter. Same here. If we pull out a random quarter as we go down, it's going to be circular. So it's going to be the same as the quarter. So these both do have the same cross sections parallel to the base as we move down the shape. So we can apply Cavalieri's principle here. So now that we got that part figured out, once again, the two things that we need in order to justify the same volume is same cross-sectional areas. And I also took area of the base and same heights. So clearly these do have the same heights because both of the stacks are made up of 23 quarters. So if you wrote that there are the same amount of quarters in each stack, I took that as being the same height, and that's why you didn't receive the full points off if you wrote that. Same cross-sectional areas, which once again, I took area of the base. That's what a lot of people were missing. So these are the two components of Cavalieri's principle to explain why a right solid and an oblique solid could still have the same volume, are that as long as the cross-sectional areas parallel to the base are the same, and that the solids have the same heights, they will have equal volumes. Finally, this question confused some people because the first part was asking you to find the total volume of 100 candles. But in the question, it tells you that this diagram here is for the candle and the candle mold. This is the mold to make the candles. But the candles themselves are in the shape of a cone. So if you're finding the volume of 100 candles, you're finding the volume of the 100 cone parts here, because the cone is what the candle is. The rest is the mold. So volume of a cone is 1/3 pi r squared height. So they tell us here that there is a height of 8 and the diameter is 3. So that makes the radius 1.5. So plugging in and putting this into my calculator, I get that the volume is approximately 18.849559215. We need for 100 candles. This is for just one, so we do need to multiply by 100. And the question does say to round to the nearest cubic inch. So after I multiply by 100, I get that the volume is approximately 1,885 inches cubed, because we were working in inches here. All of the units were inches. For the next part, we need to figure out how much it will cost to buy the wax for 100 candles. So they give us here that the weight of the wax is 0.52 ounces per cubic inch. Next to the 0.52 number, there are two units. There's the mass unit and the volume unit. So that tells us that this 0.52 number is the density of the wax. So our formula for density is equal to mass over volume. I'm going to plug in the 0.52 for density, and that's ounces per cubic inch. We don't know what the mass is. We need to find that, so that way we can find the cost afterwards. But we just found in the last part that the volume was approximately 1,885 inches cubed. You can use the rounded value in part 2 because part 1 asked you to round it. So if part 1 asked you to round it, then you can use the rounded answer in part. So in the numerator and the denominator, we have inches cubed, so that cancels out. And we are left with our unit being ounces, which makes sense because that's the mass unit and we are finding the mass. We can cross multiply. And let me put that into my calculator. I'm going to multiply 0.52 and 1885. So 1885 times 0.52. And I get 980.2 ounces. Now, this is the mass or the weight of the wax. And we need to figure out the cost. And we know that the wax costs 10 cents per ounce. So I'm just going to take the weight and multiply by the cost. So let me multiply that by 10 cents. And I get, let me just put it here because I'm running into the next part, $98.02. Remember, you're finding costs, so your answer should look like money, dollar sign, and a decimal sign, $98.02. Last part, if Walter spent $37.83 for the mold and charges $195 for each candle, what is the profit after selling 100 candles? So in order to find profit, we have to take what Walter made and subtract everything that Walter spent. And what's left over is the profit that Walter made. So first we need to figure out how much Walter made from selling these candles. So he charges $1.95 for each candle, and he sold 100 of them. So if we multiply 195 times 100, we will get how much Walter made from selling all of the candles. And that is $195. Okay, so now we need to subtract off everything that Walter spent to make the candles, and then we'll be left over with his profit. So he spent 37.83 for the mold, so I'm gonna subtract that, and that leaves me with 157.17. But Walter also had to buy the wax to make the molds. And in the last part of the question, we figured out that it was going to cost Walter $98.02 to buy all of the wax for his 100 candles. So we also have to subtract that off because that is part of what Walter spent to make the candles in the first place. So we get $59.15. And that is Walter's profit after taking away everything that he spent to make the candles.